Hi everybody. Today I'm going to talk to you guys about free body diagrams, which is a special kind of diagram that shows force vectors, and something important called the net force, which I know sounds like a force that a net would apply, but in reality it's the same kind of net as when you think about how much you actually take home from your paycheck, right? Your net pay versus your gross pay. So it's the stuff that's left over. So we're going to look for the force that's left over. We're going to do that by looking at diagrams of force vectors. So here I have a picture, and this is a lot more ornate than a normal a free body diagram would be. Um, I actually use the diagram of an actual car. So normally I would just draw a box and tell you it's a car, because that's how I roll. So anyway, I pulled out all the stops for you guys today. So free body diagrams, I want you to think about the words here. Free body is actually something that can move in any direction. So I want you to think about this car for a second. Couldn't this car move forward or backward? Of course. Couldn't this car, let's say it goes off a jump, couldn't it fly through the air? Isn't there a situation in which you could think about it flying through the air? Of course. Isn't there a situation in which maybe it would fall to a lower level? Yeah, sure. What happens if a big pit opened up underneath it, like one of those crazy sinkholes they have in Florida? Wouldn't it fall? Of course. Isn't the car free to move in any direction it wants if you took away some of the forces? Yes. And so that's what we call it a free body diagram. The body, meaning the car, is able to move in any direction it wants to. So let's look at the forces that are acting on it, and that's going to help to tell us what the motion is. Now, you have to know something important here for this situation, and that is that the motion of the car is in this direction to the right, and it is constant. Now, that constant is very important. I want you to think about inertia for a second. So let's go back just for a second and think about inertia. Inertia, this guy right here, is the resistance to a change in motion. And if you do want to change the motion, what is it that you need? Well, you need a force, and that force has to be the thing that changes the motion. Um, and if you don't have one, then there we go. So you need a force to change motion. If you don't have one, then the motion can't change. And so the question that I would have for you is this. Does that mean, since the motion is constant, that there's no forces acting on this car? Does that make any sense to you at all? That there would be no forces acting on this car? Again, this car is on the surface of a road on the earth, and it's moving forward. Does that make sense? No forces? No, of course not. There must be forces. The first force, the most obvious force to you, and the one that you should always list first, is the gravitational force. Now, of course, the gravitational force is going to act downward here. So I'm going to go ahead and put gravitational force. It's the same thing as the weight. If that makes you feel better, you can use that big W for weight. But be careful, because big W right there is also what we're going to use for work later on. And don't get confused. That's why I don't use it. If you feel like you need to use it, okay, but there's going to be some confusion later, so be careful. Okay, so a free body diagram has you find the center of mass of the object. I've drawn in a dot here for what I imagine might be close to the center of mass. It's probably a little bit lower, but that's okay. For now, it's okay. So let's draw a vector. That would be the weight of the car. Now, wouldn't you agree that the weight of this car probably is a big vector, right? So I'm going to draw it as a really long force. And it's going to act straight downward. So I did my best to draw it straight downward right there. That's the gravitational force. It's pretty close to down. I don't know, it looks a little off, but that's okay. You get the idea. It is as close to straight downward as I can get. On the Earth, it would, of course, always be straight downward. Is the car falling? No, of course not. And we can see there's this line that's drawn here to indicate the road. Looks like it's pretty horizontal to me. So let's imagine it's a horizontal road. So what's stopping it from falling? The road, of course. So let's go ahead and draw the force for the road. That force, we could put F sub road if you wanted to, but it has a special name. Anything that supports, and it supports in a perpendicular way, has a special name in physics, and you've already learned it. Yes, that's right. It's the not weird force, the normal force. There it is. Now, what do you know about the normal force and the gravitational force? They should be the same size, right? Of course, they're the same size. Why? Because the road is trying to support the weight of the car. And so I'm going to try my best to draw it to be just about the same length. Does that look pretty close? Kind of? Yeah, it looks pretty close. Okay, so here's how I draw this. I would say that we know that the gravitational force, and these bars are the absolute magnitude bars, but in vectors they actually mean the size or measurement of the vector. So the size of the gravitational force should be equivalent to or equal to the size of the normal force. Now, as long as the road is able to produce that force, you could add extra people in here, which would give it a bigger weight, which would also provide a larger normal force, as long as the road is not damaged. So the normal force actually can get higher or lower based on how much weight is being applied to it. So there's a little bit more going on to this than what we're talking about here, but for now, let's just assume that's okay. We know that they're in opposite directions as well. This one must be going straight up, this one must be going straight down. And so what can you imagine happens with a force that has, let's say, let's just give it a value, just so you can say it. Let's say it's, I don't know, 3,000 newtons. Okay, so this is 3,000 newtons up. And let's imagine this one is 3,000 newtons down. What do you think is going to happen with those two forces? Doesn't it make sense that they'd cancel each other out? And that's exactly what happens. They cancel each other out. Now, notice that they're both vertical. And so just like in our vectors and displacement and velocity and acceleration, we can isolate the velocities that are in the vertical, isolate the vectors that are in the vertical dimension and only analyze those, and then switch gears and only analyze the ones that are in the horizontal. So I'm going to change colors here. I'm going to change to green if that's okay. And so I'm going to say there's more forces that are acting here. Think about this. Is this wheel turning right here? Of course it is. Is this wheel turning right there? Of course. Are there moving parts in the engine? Of course. Is the whole car moving through the air? Of course. And so we know that there must be some force that's opposing this motion, trying to get it to slow down. And it's actually part the friction and part the air resistance. And so we know that there's a tiny force that acts against the motion of the car, trying to slow it down. And it's really made up of both the air resistance and the internal friction. I'm just going to go ahead and put a little lowercase f so that you know it's a kind of a friction force. It's what we might call either a retarding force or some sort of slowing force, right? So it always acts against the motion of the car or the motion of the object. But notice the car's motion is constant. What do we know? We know that it's resisting any changes of in its motion, and it would need a force to be able to change that motion, a force that's not balanced by anything. This would slow it down, but it's not slowing down. So if this is not able to slow it down, then there must be some additional force acting exactly opposite to it with the same size, but moving in the direction, but being applied in the direction of the car, in the car's motion. What is that force? Well, of course, that force is the applied force. That's the engine, right? The engine is applying a force to the car, and it goes in this direction right there, right? Goes in that direction. But you notice this force of friction and air resistance gets balanced out by this applied force by the engine, so that there's no extra force left over. And if there's no extra force left over, then, and only then, is the motion constant. Now, what we could say, if this force balances with this force, and this force balances with this force, is that we're in kind of a special situation. And that special situation has a special name, and it's called translational, I know it sounds really cool, translational equilibrium. Oh, I know. Everybody gets super impressed when you say it, so say it often. Translational equilibrium. And what does that mean? It means all forces cancel. And it also means, there we go, can't talk and write at the same time. It also means that the motion is constant. So if it was stopped, it stays stopped. If it was moving in this direction like the car is, it stays moving at that same speed in the same direction, just like it was before. translational equilibrium. Sorry about that. Translational equilibrium is kind of a special situation. It happens all the time. You sitting in a chair in your schoolroom, in your classroom. Bridges are in translational equilibrium. You wouldn't want a bridge to all of a sudden change its motion significantly. People standing around, all of those things are in translational equilibrium. And so what do you know about them? You don't know much, but you do know that all of the forces that are acting on them must cancel. Otherwise, their motion would not be constant. Hopefully that makes sense. We're going to do part 2 in just a minute, where I'm going to show you a situation that is not in translational equilibrium. And so that's going to be a little bit trickier because all of a sudden now you're going to have some extra force that you're going to be able to analyze. And that extra force is what I was talking about before, the net force. So next video is all about the net force. Hope that makes sense. Let me know if you have any questions.